You think you know atoms, the tiny balls spinning in your chemistry textbook, the building blocks everyone talks about like they understand them, but nobody tells you the absurd parts. Nobody mentions that the chair you're sitting on doesn't actually touch you, that atoms can be in two places at once, that they can tunnel through walls like ghosts, that measuring one changes what it does. 7 truths sit in physics journals and nobody talks about them because they break everything we think we know about reality. Which ones are real? All of them. Published research from Science Alert in 2016 confirms this isn't metaphor, it's measurement. The nucleus holds almost all the mass, packed into a space 100,000 times smaller than the atom itself. So what fills the rest? Nothing. Sort of. Quantum mechanics proved this nearly a century ago, but here's where it gets uncomfortable. If you removed all the empty space from every atom in every human on Earth and compressed us together, we'd fit into a sugar cube, all 8 billion of us. The mass stays the same. The volume collapses. Your electrons repel the chair's electrons before you ever make contact. You're not sitting. You're hovering on a cushion of repulsive force measured in the billionth scale. Research published by West Texas A&M University shows electrons in atoms spread out as 3-dimensional probability density waves. They fill the atom completely, but with almost no mass. When you touch something, you're feeling electromagnetic fields pushing back. This isn't philosophy. This is quantum mechanics confirmed by orbital imaging and electron microscopy. The Aeon essay published in June 2025 by quantum physicists dismantles the empty atom myth entirely. According to their analysis, electrons don't orbit like planets. They delocalize into continuous quantum clouds. Matter is fundamentally quantum. The so-called empty space is actually filled with wave functions and invisible quantum fields. Vacuum energy permeates everything. Superposition experiments with molecules beyond 25 kilodaltons, and Science Daily's October 2025 coverage of MIT's molecular technique for probing atomic nuclei using radium monofluoride at the collinear resonance ionization spectroscopy facility at CERN. Now back to the information. Stack 1 trillion femtometers to make a millimeter. The electron cloud extends out to angstroms. 1 angstrom equals 1/10 of a nanometer. That's 5 orders of magnitude difference in scale. Inside that seemingly empty space, quantum field theory shows us particles pop into and out of existence constantly, virtual particles. Pairs of quarks and antiquarks flash in the vacuum and disappear in fractions of a nanosecond. The proton itself isn't solid. It's made of 3 quarks held together by gluons in a space 0.9 femtometers across. Inside each proton, quarks boil in a soup of virtual particles. Antiquark pairs pop into existence and vanish. The mass of a proton comes mostly from the energy of these interactions, not from the quarks themselves. Research in quantum chromodynamics shows the quarks account for only 2% of the proton's mass. The rest is binding energy converted to mass by Einstein's equation. Pion exchange between nucleons creates the residual strong force that binds the nucleus. When physicists say space is filled with quantum fields, they mean every point in the universe has values assigned for each field. Particles are localized excitations, ripples in these fields. Particles interacting with this field gained mass. The more strongly they interact, the more massive they become. Top quarks couple strongly to the Higgs. They're heavy. Neutrinos barely couple. They're nearly massless. Pohang University of Science and Technology in South Korea publishes breakthrough findings in Physical Review Letters. Scientists watched electrons tunnel through atomic barriers for the first time. Not just pass through. They saw them loop back mid-tunnel and crash into the atomic nucleus before continuing. 100 years of quantum mystery solved with high-intensity lasers and precision measurement. Quantum tunneling defies classical physics completely. In the regular world, a ball hits a wall and bounces back. It needs enough energy to go over or break through. In the quantum realm, particles slip through barriers they lack the energy to cross. They act like waves. Their probability function extends beyond the barrier. A small part appears on the other side. The 2025 Nobel Prize in Physics went to John Clark, Michel Devore, and John Martinis for demonstrating macroscopic quantum tunneling in electrical circuits. Their 1984 and 1985 experiments at Berkeley showed trillions of electrons tunneling together through superconducting junctions. The circuit was big enough to hold in your hand, visible to the naked eye. Yet it exhibited purely quantum behavior. They used channeling nuclear reaction analysis to locate the hydrogen atoms precisely. At low temperatures, hydrogen stops hopping classically and starts tunneling. The atoms act like waves passing through energy barriers with help from phonons, lattice vibrations, and conduction electrons. Below 20 Kelvin, conduction electrons couldn't perfectly follow the hydrogen motion, and the rate decreased. The team measured these effects with femtometer precision, using techniques that bypass the small cross-section problem of detecting hydrogen. Controlling atomic behavior through quantum effects could revolutionize energy technology, but it also means the walls you trust are permeable at the quantum scale. Radioactive decay happens because alpha particles tunnel out of atomic nuclei. Without tunneling, uranium would never decay. Nuclear fusion in stars requires tunneling. Protons in the sun lack the classical energy to overcome electromagnetic repulsion. They tunnel through the barrier. Every photon that reaches Earth exists because of quantum tunneling 15 million kilometers below the sun's surface, accurate to 0.001 nanometers, 1% of atomic diameter. They nudge the atoms toward the barrier at 4 millimeters per second. This confirmed quantum mechanics predictions and ruled out alternative theories of tunneling that claimed instantaneous transmission. These qubits achieve gate fidelities exceeding 99.9%. Coherence times reach 100 microseconds. The quantum tunneling that won the 2025 Nobel directly enables the quantum computing revolution. When you erase, you apply voltage and they tunnel back out. Every photo you store exists because electrons pass through barriers they shouldn't cross. Tunnel diodes switch incredibly fast, nanosecond response times. They operate at terahertz frequencies. Applications include oscillators, amplifiers, and frequency converters. 1 microvolt produces about 483 megahertz oscillation. This forms the basis of superconducting quantum interference devices, SQUIDs, the most sensitive magnetometers ever built. They map brain activity by detecting tiny magnetic fields from neural currents. They search for magnetic monopoles. They measure quantum effects in materials. The barrier is wide and high. Tunneling probability is low. Uranium-238 has a half-life of 4.5 billion years. One atom might decay today, another might last eons. Quantum probability governs when. Without tunneling theory, radioactive decay made no sense. Classical physics said alpha particles should stay bound forever. Quantum tunneling makes it possible. Protons tunnel through the electromagnetic barrier at distances where the strong force takes over. Fusion occurs. Energy releases. The sun shines. That produces the sun's luminosity of 3.8 times 10 to the 26 watts. They watch electrons behave as waves and pass through 2 openings simultaneously. Then they turn on the observer, a tiny detector near one opening. The detector has no effect on the electron current. It just watches. When the observer's detection capacity increases, interference weakens. When it decreases, interference strengthens. By controlling the detector's properties, scientists controlled how much the observation affected the electrons. The act of gaining information disturbs what you measure. Niels Bohr derived this from quantum postulates in 1928. The measured momentum differs from the momentum after measurement. The uncertainty isn't ignorance, it's physical reality. Now measure which slit each electron passes through. The interference pattern disappears. You get 2 bands, particles. The electron doesn't decide based on consciousness. The measurement apparatus entangles with the electron's quantum state. This entanglement destroys the superposition. Freedom. The superposition doesn't actually collapse. It spreads into the environment. To us, it looks like collapse because we can't track all the environmental interactions. The phase relationships that create interference wash out. Published by Pohang University of Science and Technology's Dong-Eon Kim in Physical Review Letters, the study used intense laser pulses to induce tunneling in atoms. They tracked the electron's behavior during tunneling using sophisticated theoretical models confirmed by experimental data. But nobody knew what happened inside the barrier. The new research reveals electrons loop back during tunneling and crash into the atomic nucleus. The collision affects the tunneling dynamics. Understanding this sub-barrier electron dynamics could revolutionize control of quantum processes. Quantum mechanics builds this in fundamentally. The Heisenberg uncertainty principle states you cannot simultaneously measure both position and momentum with arbitrary precision. The more precisely you measure one, the less precisely you can know the other. This isn't a technical limitation. It's built into the mathematical structure of quantum mechanics. They don't play nicely together. When you apply them in different orders, you get different results. This non-commutativity locks in the uncertainty. Kennard and Robertson generalized this. Modern experiments with ultra-cold atoms confirm the uncertainty bound within 0.1% accuracy. They distinguished it from the uncertainty principle carefully. The observer effect refers to measurement disturbing the system. The uncertainty principle refers to fundamental limits on knowledge. Both are real, both are distinct, both shape quantum reality. But quantum computing faces a massive challenge from the observer effect. Measuring qubits disturbs their state. This introduces errors. Quantum error correction codes try to work around this. They encode logical qubits across multiple physical qubits. The redundancy allows error detection and correction without fully measuring the quantum state. These measure certain properties without disturbing others. In 2024, teams at the University of Chicago developed techniques to monitor qubit noise in real time and adjust qubits dynamically to minimize error. This addresses the observer effect directly by minimizing measurement back action. The universe doesn't have an objective state independent of measurement. Measurement is participation. Reality emerges from interaction. Until you open the box, the cat is both alive and dead. Superposition of states. The molecules weighed over 25 kilodaltons. That's 25,000 atomic mass units. They remained in superposition for more than 7 milliseconds, long enough to set new interferometric bounds on alternative quantum models. The experiment confirmed quantum mechanics operates even at this massive scale. They sent the molecules through a series of gratings. The molecules acted as waves and passed through multiple paths simultaneously. On the far side, they interfered with themselves. The interference pattern proved superposition. The molecules were heavy. They stayed in superposition. The collapse models are wrong or need massive revision. Lasers pushed the cloud up a 33-foot tall chamber and split it into 2 quantum states. The experiment confirmed atoms can exist separated by macroscopic distances while maintaining quantum coherence. Quantum entanglement is real. In November 2024, Harvard University and MIT, alongside Quira Computing, demonstrated quantum error correction on an atomic processor with 48 logical qubits. Independently, Google Quantum AI implemented quantum error correction below the surface code threshold in superconducting chips. Both teams won the Physics World 2024 Breakthrough of the Year. They made quantum computers noise-resistant by leveraging superposition and entanglement. Superposition might extend beyond physics. Published in Science magazine, research suggests quantum superposition may help plants achieve efficient energy transfer during photosynthesis. Excitons in photosynthetic complexes exist in superposition states. They explore multiple energy transfer paths simultaneously and collapse into the most efficient route. Nature highlights proposed in 2023 an experiment to levitate diamonds and test whether gravity itself can exist in superposition. If successful, this would merge quantum mechanics and general relativity, 2 theories that currently don't talk to each other. Before that, everything is maybe. Ronald Fernando Garcia Ruiz led the team at the Collinear Resonance Ionization Spectroscopy Facility at CERN. They paired radium atoms with fluoride atoms to create radium monofluoride molecules. Shane Wilkins and Silviu Marian Udrescu measured the energies of electrons whizzing around the radium atom. The molecule acted like a giant particle collider. Electrons got squeezed, increasing the chance they'd briefly penetrate the radium nucleus. But it was unambiguous. Radium's odd shape makes it exceptionally sensitive to fundamental symmetry violations. If physicists can detect an electric dipole moment in radium, it would prove symmetry breaking beyond the standard model. Extra sources of fundamental asymmetry must exist. Radium might reveal them. This validates theoretical calculations and distinguishes between competing nuclear structure models. The team produced radium monofluoride in tiny quantities at CERN by bombarding a uranium carbide target with high-energy protons and injecting tetrafluoromethane gas. Traditional nuclear physics requires massive accelerators. The relativistic heavy ion collider at Brookhaven stretches 2.4 miles around. The Large Hadron Collider at CERN spans 17 miles. These machines smash particles at near-light speed to probe nuclear interiors. MIT's molecular method achieves similar insights with lasers, vacuum chambers, and molecules on a lab bench. Next steps involve cooling the radium monofluoride molecules to reduce thermal motion and aligning them to map magnetic distribution across the nucleus precisely. Those maps will sharpen predictions of symmetry violation signals. They'll tighten limits on electric dipole moment. They'll probe why matter dominates the universe. Fundamental symmetry violations, they now have a way to carry out that search. Compact, precise, revolutionary. Radium monofluoride nuclear magnetization measurements by S.G. Wilkins and collaborators, and Physics World's December 2024 coverage of quantum error correction breakthroughs achieving 48 logical qubits by Harvard, MIT, and Google teams. Now back to the information. He proposed it as proof quantum mechanics was incomplete. John Bell proved Einstein wrong in 1964 with Bell's theorem. Experiments followed, violations of Bell inequalities confirmed entanglement is real. Distance doesn't matter. Separate entangled particles by meters, kilometers, light years. The correlation persists. Measuring both atoms simultaneously revealed wave-like superpositions. Measuring one atom alone destroyed the superposition entirely. With entangled atoms, measuring one could theoretically reveal information about the other that destroys the quantum state. Apply a magnetic field perpendicular to the magnetic direction and fluctuations occur. Increase field strength and fluctuations intensify until ferromagnetism disappears at a critical point. Matthias Vojta called it a new fur for Schrödinger's cat, a quantum phase transition not previously known to exist. If someone intercepts and measures the photons, the entanglement breaks. Both parties know immediately. Eavesdropping is detectable. Quantum key distribution provides provably secure communication. Commercial systems already exist. Grover's algorithm searches unsorted databases quadratically faster. These advantages stem directly from entangled superposition states. This represents a major step toward building the quantum internet. Published research describes quantum entanglement between photons and phonons. Light waves and sound waves connected quantum mechanically. This enables new types of quantum transducers and sensors. Change one and the partner knows. No delay, no signal, just correlation woven into the quantum fabric. Either locality fails or realism fails. Quantum mechanics says both fail in the classical sense. Anton Zeilinger closed loopholes systematically. His team in Vienna achieved space-like separation between measurements in 1998. No signal could travel between detectors before both measurements completed. The correlations persisted. Entanglement survived. The correlations remained strong. Entanglement works at intercontinental scale. This demonstrated quantum communication via satellite is feasible. What does non-locality mean? Measuring one entangled particle instantaneously affects the other's statistics. But you cannot send information this way. The measurement outcomes are random. You only see correlations when you compare results later. That comparison requires classical communication, limited by light speed. No faster than light signaling occurs. Bell's theorem proves that. Any local hidden variable theory must satisfy Bell inequalities. Quantum mechanics violates them. Experiments confirm the violation. Therefore, no local hidden variables exist. This is quantum non-locality. It's real. It's verified. It's unsettling. His particle now has Alice's original state. The original state at Alice's location is destroyed. No cloning, teleportation. Google claimed quantum supremacy in 2019 using a 53-qubit superconducting processor called Sycamore. The chip performed a sampling task in 200 seconds that would take classical supercomputers 10,000 years. Entanglement enabled this. 53 qubits in superposition represent 2 to the 53 states, 9 quadrillion states simultaneously. IBM disputes the supremacy claim but acknowledges the achievement. The problem Google solved was artificial, designed to favor quantum systems. But it proved quantum processors can do something classical computers practically cannot. That's a threshold crossing. Quantum advantage for specialized tasks is here. The universe isn't made of isolated pieces. It's made of correlated wholes. The act of measurement forces the system to assume a definite value. Before that, the system has no definite state, only probabilities. Interaction with the environment entangles the quantum system with countless environmental degrees of freedom. The superposition spreads out. Phase coherence is lost. The system appears classical. It has both equally, truly. Computers, lasers, semiconductors, MRI machines, GPS satellites all depend on quantum effects. Every electronic device uses quantum tunneling in transistors. Your phone's processor has transistors 14 nanometers wide. Electrons tunnel through barriers thinner than 1 nanometer routinely. Superconducting quantum interference devices measure magnetic fields at the femtotesla scale. Nitrogen vacancy centers in diamond map magnetic fields inside living cells. These protein qubits have metastable triplet states, similar to nitrogen vacancy centers in diamond. They measured magnetic field signals with up to 20% spin contrast in bacterial cells. Chinese Academy of Sciences produced the first two-dimensional sheets of metal in 2025. Published in Physics World, Guangyu Zhang and Luojun Du created true two-dimensional metallic layers. Most two-dimensional materials are held together by van der Waals forces. Easy to exfoliate, metals have different bonding. Creating two-dimensional metal required breakthroughs in synthesis. Takamasa Momose and Susumu Kuma observed superfluidity in molecular hydrogen for the first time. Published in Physics World Top 10 2025. They can find hydrogen molecule clusters inside helium nanodroplets, embedded methane molecules within clusters, and monitored methane rotation. This detected superfluidity onset. 20 years of effort paid off. Molecular hydrogen enters superfluid state between 1 and 2 Kelvin. Below its freezing point of 13.8 Kelvin, they kept it liquid and measured the quantum phase transition. They change when observed. They fill space with electromagnetic force while being almost entirely void. Touching means changing. You cannot separate observer from observed at the fundamental level. When electrons briefly enter this nucleus and sample its structure, they pick up information about charge distribution and magnetic moment that reveals the violation of symmetries physicists thought were inviolable. Inside radium monofluoride molecules, electrons now carry messages from the nucleus, showing us exactly how nature cheats its own rules. Matter 1. Antimatter lost. Atoms tell us why. We just learned how to listen.